Okay, let's do another example. This time a little bit different result of sketching our rational functions. So we still have the same four things that we're looking for. We still have to find end behavior, which is that ratio of leading terms. So it'll be that a sub n x to the n over b sub m x to the m. And then we'll still need what? We'll still need to find our y-intercept, which would be f of 0, right? And then we'll still need to find our x-intercepts, if they exist. And that'll be f of x equals 0, solve for x. And then we're going to have to look at our discontinuities. So find our discontinuities. And those would be removable or non-removable based on whether or not we can cancel the zeros out of the denominator or not. And so those are kind of the four stages that we need to go through to find the information we need to be able to sketch this thing without the calculator, and then test ourselves with the calculator, see if we did a decent job. All right, so let's take a look at part one. Part one, we need the end behavior. So end behavior. And for it, I'm looking at the ratio of the leading terms. So the leading term of the numerator is just x cubed, and the denominator is just x squared. And so this one's relatively straightforward. Now, what did we say? We said that if my m, well, in this case, my n, is greater than my m, right? My numerator's power is greater than my denominator's power. And that left us with unbounded growth, because the number of pieces is growing faster than the size of the pieces. And so that means that we're headed towards infinity or negative infinity as far as our end behaviors go. So what we do is we simplify this. And when we simplify that, it would be x to the 3 minus 2. So it's going to be x. And this is so if I want to interpret this is a positive x to the odd. And that means that it has the shape of an x cubed function as far as the end behaviors go. And so that means as x approaches negative infinity, y also approaches negative infinity. As x approaches positive infinity, y also approaches positive infinity. We call this the left end behavior. We call this the right end behavior. Okay. And so that's my end behavior for this function. Now, I need to find my y-intercept. Right, my y-intercept is nothing more than, we should write it down, y-intercept. That is f of 0, because I'm looking for the place where my function crosses the y-axis. Well, that happens when I haven't moved from left or right away from the y-axis. That happens at an x value of 0. So that's why I'm putting 0 in for x, to find out where I am on the y-axis. Okay, so if I plug in a 0 into this original equation, oh, that's interesting. So if I put 0 in here, what am I going to get? I'm going to get a 0 cubed plus 2 times a 0 squared minus 3 times a 0, all divided by a 0 squared minus 25. And so I end up with 0 over negative 25, which is just 0. So I do have a y-intercept. It just happens at the origin. So my y-intercept equals 0. Okay, now I need to find my x-intercept. All right, so let's do 3. 3 would be my x-intercepts, if they exist. There might be one, there might be none, there might be many. What do? I take my numerator, my x cubed plus 2x squared minus 3x. I set that equal to 0, and I solve for x. That does not look like fun to solve for x. How do I remember what to do here? It's a cubic. I've only given you one set of tools to solve a cubic with, and that's to factor it into simpler equations using principle of zero products. And so what we really need to do is principle of zero products. Which basically means leave the zero on the right-hand side and try to factor this into where it's all multiplication. And once I can accomplish that, I can break those factors up into separate equations equal to zero. Well, the first thing I spot is there's an x in all three of those terms. And so I can pull an x out of all three of those terms. I'm left with an x squared plus a 2x minus a 3 equals 0. And if this is going to factor, it's a trinomial quadratic form with a 1 in front of the x squared. If that's going to factor, it'll factor into two binomials that start with x, right? Because if I do f of FOIL, I do first, which is x times x, which gives me a 1x squared. Now I'm looking for two numbers that multiply to be my -3 and add to be my +2. And that sounds an awful lot like a 3 and a -1. Because 3 times -1 gives me -3, and 3 minus 1 gives me a +2. So that'll give me a +3 and a -1. And all of a sudden, I have one term here now with 3 factors, and that equals 0. Now I can make a new equation for each factor. So I have x equals 0, or x plus 3 equals 0, or x minus 1 equals 0. Because if x minus 1 equals 0, it really doesn't matter what those two are. 0 times them will be 0. That's that whole principle of zero products idea. Okay, well, I got x equals 0. That's already solved. I got to subtract 3. So now I have x equals -3. Or, and I got to add 1 here. So x equals 1 and x equals 0. We're just going to copy down for consistency. And so those are my 3 x-intercepts, my 3 zeros. And then I need to check each of these has an understood power of 1 here, right? And that means there's only one copy of that 0 sitting there. And so we say that this has a multiplicity of 1. This has a multiplicity of 1. And this has a multiplicity of 1. For each of those zeros. If I have an odd multiplicity 0, it passes through the axis. If I have an even multiplicity 0, it bounces off the axis. And that's why I'm being so careful to identify not only the 0, but also the multiplicity of that 0, because it changes the behavior of the graph as it goes, as it works around that axis. Okay, and so now we need to think about 4. All right, 4 with my domain restrictions. Thinking holes and asymptotes, removable or non-removable. So removable or non-removable, which are holes or asymptotes. Okay. Well, the way I got to check that is I got to see if I can simplify this original equation, this original function. And so my original function, f of x, it equals, I'm going to use the factored form of this. Then I have x times x plus 3 times x minus 1. And then that was all over x squared minus 25. And so x squared minus 25. Well, that's the same as saying x plus 3, x minus 1, all over x plus 5 times x minus 5, because that's the difference of squares. Nothing simplifies. No zeros cancel out. And so there are no holes. There are no removable discontinuities, no holes, because nothing simplifies. So any zeros that are left in the denominator are non-removable discontinuities. They're asymptotes. And so now I take that whole denominator, the x plus 5 times x minus 5, set it equal to 0, and solve for x. Well, this is just another principle of zero products problem. And so I have x plus 5 equals 0, or x minus 5 equals 0. And so I have x equals negative 5, or x equals 5. And these are each, again, that understood 1 power here. These are each multiplicity 1. Multiplicity 1. And so those are where my vertical asymptotes, so vertical are at those locations. All right, I should have everything I need to sketch this function now. And so I'm going to make myself a nice big coordinate system. And what did I say? I said that my end behavior was positive odd. So left was negative infinity, right was positive infinity. And so I just kind of like to put a little notation here just to remind me where I'm going in the end. Okay. Then I said my y-intercept was 0. And so I'm going to put a dot here at 0. And then my x-intercepts were at 0, negative 3, and 1. And so I've got 1, 2, 3, and 1. And so negative 3, I already had the 1 at 0 because it was also a y-intercept, and the 1 at 1. And so now I have negative 3, 0, and 1. And then I had vertical asymptotes at negative 5 and 5. It's negative 3, negative 4, negative 5, and then I dot in my vertical line here. Then 1, 2, 3, 4, 5. And I dot in my vertical line there. And the best place to start here is probably just coming in from the left. Because if I come in from the left, I know that I have to start from down at negative infinity. And I come up, I come up, I come up, and I can't go up here. I can't approach that asymptote for this direction because I don't have a y-intercept there, or an x-intercept there. And so since I can't cross that x-axis, at some point I have to turn back around and approach that vertical axis, that vertical asymptote in that manner. Now, this was an odd multiplicity 1 asymptote, just like this was a multiplicity 1 asymptote. And so if I went down towards negative infinity on the left side, as I approach it from the right side, I have to go up to infinity, right? Remember, opposite behavior. And so I have to approach that vertical asymptote from that direction. Now, all 3 of my zeros were odd multiplicities, right? M1 for 0, negative 3, and 1, which means it's going to pass through all 3 of those zeros. And so we're going to come down, we're going to pass through, we're going to turn around at some point, we're going to pass through, we're going to turn around at some point, we're going to pass through, and I know that I don't do this and approach the asymptote from that direction because I can't cross the axis again. And so I must approach that vertical asymptote going down toward negative infinity. Otherwise, I'd be having an additional 0 that I know doesn't exist because I've already calculated and found all of my zeros. Well, it's an odd multiplicity vertical asymptote, which means from the left, if it goes down to negative infinity, then from the right, it better go up to infinity, which is good. Well, we'll see why it's good in a second. All right, so I've gone up towards infinity, approaching that asymptote, and then at some point I turn around and go up towards infinity. And the reason I said it's good is because I can't cross the x-axis over here. I know there are no x-intercepts over there, And so this thing better turn around before it gets down to that x-axis. Those of you who have done this before will notice that I'm ignoring what's called an oblique asymptote. And there's another class of asymptote in here called an oblique asymptote that basically would denote the slope of the line that this thing is going to look like it approaches when we graph it. And I'll go ahead and tell you it's going to be a slope that kind of goes through here and looks like it has a slope of 1, okay? And that's my oblique asymptote. We're not going to focus on oblique asymptotes for the amount of time that we have left to do this sketching. So that's something that we're gonna leave out of this section. Is we're not going to worry about oblique asymptotes. All right. So if I go do my graph, I want to see if I get anything that looks similar to that. Now there are things that we just don't know. We don't know how far down that comes. We don't know how far down that goes, how high that goes, how far down that goes. We don't know how aggressive some of this behavior is, and so some of this we cannot know without calculus. And this being an algebra class, we just can't know that. But we can get a good start. We can get an idea of what the sketch looks like. We can just do a lot better job once we understand calculus. All right, so let's type this in as it was originally to our calculator. So I have an x cubed, and then plus 2 times my x squared minus my 3 times my x. And I'm going to divide by, now I'm going to have my x squared minus a 25. Hit enter. We'll go with that window for now because, most of the interesting stuff happens right between -5 and 5. And then we've got to be able to see what happens to the left and right of -5 for the asymptotes. And so let's hit graph and see what happens. The moment of truth. You look at this and you look at my sketch and they don't look the same. And so the question is, am I wrong or is the window wrong? The window not making it look like I'm right. Oh wait, that starts to make me look like I'm right, doesn't it? Because my zeros are in the right place. And that even looks an awful lot like what I sketched over there. And I promise I didn't type this into a calculator first. All right, now if I zoom out, I've zoomed out too far. There we go. Let me zoom out in the y-axis as I zoom out in the x-axis. What do you know about that? It's almost like I have an idea what I'm talking about. Even talking about that, if I get my boxes here to where they're about the same size. I even said that we were going to have a oblique asymptote with a slope that looked about 1, right? And that oblique asymptote does look like it has a slope of about 1 if you take a look at the scale now. And so we're not as interested in about that, but it is there. All right. I hope that helps us as we do more of these sketching rational functions by hand and as we prepare for our final.